Okay, welcome back. This is a very short section again, so I will be linking another video that will maybe make this a little bit more clear what the section's trying to say. Just because the book kind of talks about one thing and one thing only, and that's that an inner product space is just a vector space that you also happen to have an inner product on. Now, because it turns out that there are vector spaces that we cannot define inner products on. I actually mentioned that very briefly in my addendum video a couple days ago that was dealing with the space of analytic functions. So those functions you can't define an inner product on. But if you can define an inner product on a function space like we did in the last class, then we call that an inner product space. And in fact, we call it a Hilbert space, which is this word that you're basically going to be using for the rest of your careers in any sort of solving differential equations sense. So especially if you go into physical chemistry or physics, you're going to be using the Hilbert space basically the rest of your careers. And Hilbert spaces are inner product spaces that are called complete. And I think I mentioned that too in a previous video, where complete just means that there's not, if I decide to take a sequence in the space that where the distance of the sequence is actually going to zero, the distance between elements of the sequence tends to zero, then that there's actually somewhere that the sequence is ending up. Or in some other sense, if I take steps somewhere and I start taking infinitely smaller and smaller steps, that eventually I stop at a point which itself is actually in the space. Like there's a function there that I'm going to be approaching if I take infinitely small steps. You don't want to fall into a hole, more or less. So these are the sorts of spaces that we're thinking of, and it all revolves around this idea of a Cauchy sequence, which apparently you talked about last semester. It's not something you should put too much effort into. It's the sort of thing that most math majors probably couldn't tell you what they are. I can definitely talk about Cauchy sequences all day long, but I think most people don't worry too much about Cauchy sequences because I'm just going to scroll to the bottom. Take completeness of any space as given. Okay, so you just assume that all of the spaces we're working with are complete. It turns out that mathematically you can always complete a space anyway, so there's not really a reason to not work in a complete space. And so for things like that, we're just not going to worry about really this section at all. Just think about an inner product space as a vector space of functions, which also has an inner product on it, like we were talking in the last section. And then a Hilbert space is one of those that is complete in the sense it doesn't have holes. There's not an absence of some function somewhere, which you really have to be contrived. Somebody would have to work pretty hard to basically create a hole in a function space. And so don't worry about completeness. Hilbert spaces are inner product spaces. That's what you want to think. They're infinite dimensional. They consider functions. Solutions to many differential equations are in Hilbert spaces and stuff like that. So it's just an infinite dimensional inner product space. That's what you want to think. This, you can go ahead and read the example if you want, but I wouldn't worry too much about it. Anyway, I'll link another video. I hope you enjoy that, and bye.